Hey everyone, how's it going? I'm Matt here with a checklist video about stacks, queues, and heaps. So what this video is meant to do is go over the key points that you should really understand about these topics um, and not really teach these topics, right? So if anything here is confusing, it's a sign that you need to go back, review this stuff, ask for help from your instructors, your TAs, the rest of the cohort, um, or go back and revisit the reading material that we've assigned. So the first thing you should definitely understand are the properties of these data structures. So a stack is a last in, first out data structure. When you pop from a stack, the element that gets returned is the last element that you inserted, right? So the last thing that goes in is the first thing to go out. For a queue, the when you pull, the element that's returned is the first element that you've put in, right? So first in, first out, right? Another way of saying this is in a stack, what's returned is the newest element, and in a queue, what's returned is the oldest element. For max heaps and min heaps, these are the data structures we use to implement priority queues. In a max heap, every node is bigger than its two children, right? So a max heap is a heap kind of by consequence that when you pull from it, the element that's being returned, the element at the root of the heap, is the maximum. The min heap is a data structure, right, where it's the inverse. The element that gets pulled is the minimum. The element at the root is the minimum. Now, when I say a root and children, it's probably useful to visualize that, and you'll see a visualization of that in a couple of slides. The next thing you need to make sure that you understand is for stacks and queues, there are a couple of implementations that we can go with, right? And in an interview, it doesn't really matter which one. It's important just to kind of tell the interviewer you're doing one or the other. So you can implement stacks and queues using linked lists. This is what Gail does in the video that we've shared. But you can also implement stacks and queues using a dynamic array. And I'll go over that implementation once more because it is an area where people tend to have some difficulty. I'm going to switch to my notebook and go over really quickly how you implement a stack using a linked list visually, right? The first thing to keep in mind, both for stacks and queues, is the head is always pointing to the next element to be returned, right? So let's consider a stack here, right, where we have one, and that's the head and the tail. Right now we just have one element, and we're going to add a second element. We want the head to always point to the next element to be returned. So in that case, I make my head point to this 2, and it needs to stay being a list, so I attach this 2 to the 1, right? So for a stack, right, when I come to pull, the head is pointing to the 2, so I can, actually let's add another element, right? Let's add a 3, so it's a little bit more of a realistic example, right? So let's say I have a head pointing to a 3. Again, I added it to the from the left, right? I started attaching to the head, right? The head is pointing to the next element to be returned, which is the newest element. So when I return, I can just return 3, and I can make the head whatever the next element is. Right, that's how a stack is implemented using a linked list. Again, if this is confusing, please go back and watch that video that we've shared. Now, for a queue, it's the opposite, right? We want the head to continue pointing to the oldest element, right? So when I add the second element, I just add it to the tail, right? And for me, this is a more intuitive one. This is really how it works, right? When you're appending to a linked list, right? So I keep adding to the tail. Now, again, it's the same thing when I pull. I return the 1, right? This time I'm returning a 1 and not a 3 because it's the oldest element that gets returned, right? And I increment the head to point back to the 2. right? So that's how you implement a queue using a linked list. All right. So the next thing is how we implement a stack using a dynamic array, right? And a queue using a dynamic array. So coming back to my notebook, right? I'll just add in the indices right here because I forgot to do that. I'm going to add let's say I have a stack that has 1 again. I push another element, right, 2. I push a third element, 3, right? When I want to pop, I just pop from the right, which is whatever the last element in my list is. That's the top of my stack, right? So it's really easy, right? I push, I fill from left to right, and then when I pop from the right. All right, so that's pretty straightforward. Obviously, if I fill up my array, as you remember from your previous session, then this is a dynamic array. So I have to fill it up and put it into a new container, right? That's what happens when I want to, let's say, add 6. Right, again, that's just what a dynamic array is, right? Now let's consider a queue, right? So again, I do 1, 2, 3, but this time I'm polling from the left, right? So I need to have some pointer for the first element, right? I need to have some variable that just tells me, okay, where is the first element? Because now when I poll and I get rid of this 1, the first element is, I need to know that the first element is not at index 0, it's at index 1, right? Now let's say I keep adding some elements. So I add 4 and 5, and then I poll, right? And then I want to add a sixth element. Now, I could go ahead and add everything to a new array, but notice that these things are act these slots are actually empty. Like we're not using them, right? So the fact that the first element now starts at index 2, I know that the elements at index 0 and 1 are free, right? So when I want to then add the next element, I can just do a wraparound. I can just say this array, consider it to be a circle, right? So the next element I add is going to be um, at index 0. And so the way I would do that in terms of math is I take, right, my first element, well, the index of my first element. So that's going to be here, it's going to be 2, for example. And then I add the number of elements that I'm currently storing. In this case, right, that's going to be n, I'm going to call it. And n is going to be equal to 3, right? So then, in this case, right, I would do 2 plus 3. That gives me 5, but 5 is out of bounds for this array. And I would just do a modulo with the size of the array here, which is also 5, right? So this is 5, right? Because I have 5 slots, right? And this is what's known as a wraparound, right? So in this case, I do 2 plus 3 modulo 5, and you'll see that back, that gives me 0. So I would add 6 to 0. And then we kind of keep doing this, right, when we're adding until n is equal to the size of the array. At that point, I have 5 elements being stored, and that's when I move to a bigger array, right? So I expanded on that um, a little bit longer than the other things because that is an area where people tend to get confused. All right. So now the next thing that you need to know is the runtimes for each of these operations. So for stacks, right, whether I was doing the linked list approach or the dynamic array approach, when I push, it's just appending something, right? Which is an O of 1 operation. When I pop, again, I'm just manipulating some pointers, which is O of 1. And when I peek, right, just look at what the next element is. That's obviously O of 1. You just have a pointer to the next element. It was the head in the linked list. It is the rightmost element in the array list. Um, so that's all O of 1. Similarly, for queues, right, it's O of 1. Now, in the case of array list, remember that adding, yes, sometimes you will move to a new bigger array, but that's going to be an amortized cost, right? So we still consider the add operation to be O of 1, even in the dynamic array case. All right, so stacks and queues, all these operations are O of 1, right? Um, which is pretty neat. Now, going back to heaps, here I have an example of a max heap. Right? So as I was saying earlier, the root is the largest number, and every single node has the heap property. In this case, it's the max heap property, saying that as a parent, I'm bigger than my two children. So 19 is bigger than 17 and 3, 17 is bigger than 2 and 7, etc., etc. Um, Now we can represent this heap obviously as an array, and I'm not going to dig into that, but it's definitely important if you don't understand how to do that to really reread that Geeks for Geeks tutorial about how we use array representations for heaps, right? Now, when I add a new element, I'm going to add it to the next available position, and I'm going to have to heapify it up. All right. So that's going to be I'm going to have to flip it, right, from the bottom to the top, right? So that is going to be a logarithmic time operation. Now, I would normally say, right, it's really important to know why it's logarithmic time, but for now, it's fine, in my opinion, to really memorize that and revisit this concept once we get to trees, right? Because as you notice, the heap is a form of binary tree, right? So we really go into more details about why it's logarithmic time once you get to the tree um, section, right? So in the case of heaps, adding a new element is logarithmic time, polling an element is logarithmic time, and peeking at that element is a constant time operation. Again, peeking is kind of nice, right? You just have a pointer to the thing you're looking at, and you're just returning that value. Um, Finally, one last point that it's really important to know is that there's a way to build a heap with n elements in O of n time, right? Normally you would think that if you add an element, right, I'm adding n elements, each element, the offer operation is log n, you would think it's n log n runtime. But there's a build heap technique, right, which is O of n time. And I'll let those of you who are interested really read more about that technique and why it is that it is an O of n time. And it has to do with some math, right? So but the idea, at a very high level is for build heap, you have a list of a bunch of elements, and then you just keep, you dump all the elements into the heap rather, right? So you have a heap with a bunch of elements, and they might not necessarily follow the heap property, and then you just heapify all the elements. You keep flipping these elements until you turn it into a valid heap. Again, those details are kind of uh, too much for this video, but I do encourage you to go look at that. That's all. If anything was confusing about today's video, please do let me know. Please do let your instructor know. Please do let your TAs know. The key to success here is really to reach out for help.